institute that I really am from is from the Karl and Emily Fuchs Institute of Microelectronics. So my name is Trudie Joubert. The Karl and Emily Fuchs Institute for Microelectronics, short we just call it CEFM. So the first bit that I'll be talking about is just what is microelectronics about in memory. And I call it in memory because it's alliteration, but where I'm really going is just the history. Okay, so it started off with the best Christmas present that changed the course of history. And this was, of course, the invention of a transistor. And this happened in Bell Labs in 1947. It wasn't quite Christmas, it was the 23rd of December, but it was close enough. So one of the things I do want to point out, so that's the image there on the left-hand side, is it's quite rough. It's not a very nice device, well manufactured in an expensive facility. So that's kind of the first thing that I want to point out. Many things have happened to that kind of device in the meantime, but we're still making devices that look more or less like this as we speak. Okay, so the three people, Bodine is the person sitting, and Bratton is the person with the glasses in the background, and Shockley is the grey-haired man standing in the background. They were awarded the 1956 Nobel Prize for Physics for this specific invention. Just another interesting snippet, the three of them, they did not stay together at Bell Labs. Bratton stayed at Bell Labs, Bodine became a professor, and Shockley started his own company. Okay, so that's more or less anywhere people can go after an important invention like this, they did. All right, so the next invention that was important, integrated circuit. So the left-hand image is an oscillator circuit, and it contains 5 components, not a single one, so 5 components. Once again, quite a rough device. Jack Kilby, he's the man on the right-hand side, Texas Instruments. He won the 2000 Nobel Prize for Physics. There is a lot of time that was spent doing other things, fighting about it, deciding who actually did what, things that happened with patents and IP and things like that. But eventually they decided that Jack Kilby is the person who would receive the Nobel Prize for that. A very important one is planar integrated circuits. That was invented in 1959. Robert Noyce, he did not receive a Nobel Prize for this invention. He was at Fairchild at that point in time, Fairchild Semiconductor. He was also one of the founders of Fairchild. He was a co-founder of Intel. He was a co-founder of IBM. He was a co-founder of all kinds of places, involved with many things. So the example on the left-hand side is the first integrated circuit. It's based on oxidation of silicon, so we're basically making layers and then removing partial, or using a mask to partially remove some of those layers, subtractive manufacturing. And this has of course been going on for many decades. So this is more or less the process that is followed to manufacture integrated circuits. On the left-hand side is in silicon ingot. So this is a single crystal cylinder. And what's interesting is that photograph that I have just to the right-hand side of the ingot. There are 2 people on the photograph that are quite easy to recognize. And in between them, there's a shiny cylinder. That is a single ingot of single crystal silicon. It's amazing if you think about it. It's wow, indeed. And those are then basically sliced. Diamond saws used to slice them into wafers. The manufacturing happens on the surface mostly of the wafer, in layers with subtractive manufacturing processes. They are sawn apart. You get dye from that. And these are then packaged. Because each of those processes are a manufacturing industry all on its own. So on the materials side and manufacturing the ingots is an industry. The actual manufacturing of the integrated circuits is an industry, and packaging itself is also a huge industry all apart. Okay, I think most of you might have heard of Moore's Law. Gordon Moore, in 1965, he wrote a paper for Electronics magazine. It was called Cramming More Components onto Integrated Circuits. And in that paper, he predicted that the number of devices, and particularly the cost, it was related to the cost, would double every year. Which was not, he later updated it a little bit, it became doubles every 2 years. Another person said it's every 18 months, so it's been tweaked a little bit this way and that, but Moore's Law still holds today. And of course, it's a situation where if you have a law like this, it becomes a target. It becomes a self-fulfilling prophecy. Right? Engineers work to fulfill Moore's Law, but they've been managing all the way. So this is a typical graph. This one is interesting to me because it includes devices from before Moore stated his law. So this is mechanical devices, relay devices, vacuum tube devices, and then we get to the transistor and the integrated circuits. And Moore's Law, that's on a log scale, it holds. It still holds today. But there is a problem with that, which I will discuss in a moment or two. For now, here is just a few things that had happened along the way to enable Moore's Law. So the CMOS process, which is something that I've used extensively my whole life. The invention of DRAM. We all know DRAM because there is RAM in our, so the D stands for dynamic. There is RAM in all of our computers, and we still use that. That was IBM. You'll see IBM appears quite often. The UV excimer laser. Photolithography is the process that's used to transfer the mask onto the wafer so that you know which parts to remove and which parts to leave there. Later on, it's like almost 2 decades later, so between 1982 and 2006, we were still looking at excimer laser photolithography, but this time deep UV, basically very, very short wavelengths. The shorter the wavelength, the smaller the features that we can make with it. Memristor is another interesting device. The others I put in italics because those were more lab-based work, so it's research work rather than directly implemented precisely like that. So there's silicon and germanium, so we're beginning to move into other materials than just silicon. Also 3,5 materials like gallium arsenide you might have heard of. This one is super cooled, but it goes to 500 gigahertz. It's an amazing device. There's a nanowire transistor, so no longer a junction, it's a wire, and the device is all around that wire. Single atom transistor, so it's one atom sitting on a surface, working like a switch, which is also very, very impressive. And now we get to the problem of Moore's Law, because the other side of Moore's Law says to be able to make all those wonderful and amazing devices, we need more expensive fabrication facilities, which take longer to develop. And the effect of that is that there are fewer and fewer companies globally that can actually manufacture the newer nodes. We're literally down to 2 at the moment. Okay, so where does this leave South Africa? Where does this leave us? If many of the first world countries cannot afford the newer fabs, there is no way that we can. So manufacturing these, and I call it more devices, it's just not something we can do. It's not something we can play in. It's not a field. So if we look at the more nodes, so this is just the sizes, the minimum size of the feature that you can make. Between 10 micron down to 5 nanometers, which is more or less where we are at the moment. The years, so we're ahead of that 2020. We can already make 5 nanometer transistors. So those were the years, more or less, when these technology nodes were introduced. Those two green arrows are where South Africa still played, manufacturing in this game. Okay, so the 6 micron node, we had a research lab at the Carl and Emily Fuchs Institute of Microelectronics, and it was the foundation that had donated the funds for us to put it up. Okay. We made very interesting things in that fab. Unfortunately, literally last year, 2018, we broke everything up. We simply could no longer maintain it, and even the layers that we could still make and use to do devices just no longer were worth it. Okay. The other green arrow, that was a commercial fabrication facility that had a 0.6 micron process. They closed down in 2009. So basically when it was introduced in 1994, and we could do interesting and commercially viable products with that until 2009. So one of the messages that I want to give from that is we don't necessarily need to play right at the front edge of the technology. We can do a lot with older nodes. So the 600 nanometers may be not good enough, but then there are some others that are. And if you think about globally, there are huge companies that no longer have their own fab. So they themselves have become design houses, fabulous design houses. And there is absolutely no reason whatsoever that we here in South Africa cannot do it. So we design. Some of the interesting things, so this is it wasn't a South African statement, it's a statement that holds for the whole world. CMOS, so that's the technology that I've mostly been working in, is what was used to make processors and memory and the things that we know about that go into computers and cell phones and things like that. But there are other interesting applications. And one of the ones that they are talking about is sensing. And this of course fits into the whole idea of the Internet of Things. If you have Internet of Things, even Internet of People in the end, you need sensors to do whatever you need to do. If you want to monitor something, you need a sensor to monitor it. And we need many of them. Otherwise, we're not going to make an Internet of Things and an Internet of People. So that's the one trend that is important globally, but also important for us. And the other one is heterogeneous components. Now, as I speak on, it's like hybrid integration using different technologies. So I'll give you some examples of some of the things that we do. But once again, the last sentence where it goes, growth is expected in wearable devices, medical diagnostic devices, and the Internet of Things. There it comes again. Okay. So those are the kind of things that are important to look at. And I fully believe in using appropriate technology. You don't necessarily need the best of the best of the best to solve a problem. You need the right technology for the solution of that problem. And some examples, and these are now in South Africa. So these are some of the things that we work on. On the left-hand side is an image near the Yixkay River, so that's close to where I come from. It's the separation between Pretoria and Johannesburg, which are actually two different places. Many people don't believe it, but they are. And what we see here is the river itself is a total mess. We also see on the left-hand side the bank is a community that is not very affluent. While on the other side of the bank, you can see in the distance is a community that is very affluent. And we have to cope with situations like this. We have to do monitoring. The affluent society might be able to afford very expensive ones, which anybody in the world can do. The ones on the other side cannot necessarily. We are in a unique situation where we can make a contribution to a problem that is local. We know this problem better than many of the other people in the world. And we should take advantage of that to develop low-cost devices, which is kind of where I'm going with this whole thing. The other pictures are just, one is a huge hospital, it's Baragwanath Hospital. And some of the things we see are people waiting in hospital, and sometimes they wait days. Sometimes they come and spend the whole day there and cannot be helped. On the other hand, and it's also a waiting problem, but it's a completely different waiting problem, is that's somewhere in rural KwaZulu-Natal, where there's a dirt road going to the local clinic, where people have to walk to get to that clinic. They sometimes have to walk the proverbial half a day to get there. Then they have to go home. Sometimes blood tests are done, and it takes a week for the results to come back, which is a problem, because then they have to walk the proverbial half a day again just to get the results. And in the meantime, they may have keeled over and died. It's really as bad as that. So those are some of the problems we're looking at. Challenges. The other flip side of the coin is just the challenges and opportunity to do something about it. So where is microelectronics going? We're talking about manufacturing of microelectronics. Where is it going? Particularly in South Africa. We often talk about straddling the chasm, and it's particularly the innovation chasm. So it's we do research, and then there are supposed to be spin-off companies that commercialize it, and somehow there's a disconnect between the two. So that's kind of the main chasm people often talk about. But there are some other chasms as well. Some of them have to do with technology scale. So some things are meters big. An example is we can use tiny devices to make a display that's a wall big. So it's meters while also doing devices that are nanometer scales. Yeah. All in the same device. So it's going from nanometers through micrometers, millimeters, centimeters, going up to meters. These problems require interdisciplinary work, even transdisciplinary work. The things I'm working on require electronics, chemistry, materials, biology, if we do biosensors, many other interesting things that we can include in these same devices. And then, of course, the last one is the innovation chasm, which is usually the context that this is spoken about. Important bit, technology push. I'm on the research side. I work on technology. I like new things, but that doesn't necessarily solve the problem. The other side is the demand pull. Sometimes you have the problem and it asks for some kind of technology that doesn't exist yet. So there are these two forces, and we must try to work in the sweet spot where those two meet. It's kind of where the red star is. And so that's where we're going with microelectronics. Okay, so just a little bit of background in terms of CFM specifically. So that's the institute where I work. The image on the left top is just above our front door. So there you can see it's the Institute of Microelectronics. This is the history of CFM. So this is looking back. It's what is in memory, things that we have been doing before. The focus areas: mixed signal integrated circuit design, novel electronic devices, RF, so that's radio frequency microelectronics. We looked at MEMS. So that's a mechanical and electrical combination device. And then we looked at quite a lot of photonics and optoelectronics. So many of our devices were either photodetectors or even sources, light sources. Those were the kind of things we were working on. Around the edges, you'll see some images. The one bottom left, that's an example of a wafer in a boat in the fab that was inside CFM, where we really manufactured these devices. So most of the images, all the images you see on this page, we made in CFM, apart from one, and that's the wafer. So that's the big one with a white frame, the round wafer. That was manufactured elsewhere. So the two devices, if we start 1 o'clock, that's an RF device. Then there's a MEMS device. The one below that is actually the biggest CMOS design that was made in our own facility.